Hello everyone, in this class we are going to discuss about the cantilever beam problems, which is going to the undamped condition, free vibration signal level of freedom here. So this is the next problem. Determine the natural frequency of the cantilever beam, which carries the load at W at the free end through a completely spring with the stiffness K. So spring stiffness is K and beam stiffness will be the KB. The beam has a uniform cross section and its flexural rigidity is given by E and neglect the mass of the beam. So this is a kind of the small kind of the derivation to identify the completely natural frequency and time period for the cantilever beam. It is carrying at the edge point load. So cantilever beam and coil spring both are connected to the series condition. So we can use the formula of the 1 by Ke is equal to 1 by K plus 1 by Kb. Here Ke means total element complete beam plus spring total stiffness. K is defining the stiffness of the spring here and Kb is defining the stiffness of the beam. So for cantilever beam load, we have the free end deflection maximum formula. Delta is equal to WLQ by 3EI. So stiffness of the beam formula we know capital W weight of the beam by deflection. So deflection value substitute here W by WLQ by 3EI. So W will get cancelled here. We'll get the stiffness of the beam Kb is equal to 3EI by LQ. So when we know stiffness of spring plus stiffness of the beam, we'll substitute in the series formula here. 1 by Ke is equal to 1 by K plus 1 by, in the place of Kb, we are substituting 3EI by LQ. It is already in the denominator, so the numerator will go to the denominator here. So 1 by K plus LQ by 3EI. So 1 by Ke is equal to, we'll take the LCM here, 3EIK. So we'll cross multiply 3EI plus KLQ. So Ke is equal to 3EIK by 3I plus KLQ. So this is the stiffness of the total element of the cantilever beam here. So in this one, by using this value, we'll find out the first natural frequency. Omega is equal to square root of Ke by m here. M means we know weight by gravity. So when you substitute here, Ke formula this one and W by G. So G will go into the numerator here. So natural frequency. So F is equal to omega by 2 pi, which is reciprocal to the time period. So F is equal to, you get this kind of number. So in the next one, the same mathematical model can solve this problem. Determine the natural frequency and natural period of the system consisting a mass of 100 kg. So they given the m value and attach it to a horizontal cantilever beam through the linear spring K, and the cantilever beam has a thickness of 0.8 centimeter. So they given the length of the beam and width of the beam and thickness also. So we are taking E value 2.1 into 10 power 6 kg per centimeter square, and they given the spring stiffness K is equal to 10 kg per centimeter. So there is nothing to change. In the previous derivation we can go to the same thing, but values is going to be changed here. We are going to substitute the values. So for cantilever beam, load at the free end, deflection WLQ by 3I. So for this one, first we had to find out the I value because they given E already. We know the W, weight of the beam, and L value also. So I is equal to VdQ by 12 because the beam is in the rectangular shape, and for that one moment of inertia is equal to VdQ by 12. So B is equal to nothing but thickness 0.8 into D, depth 1.2 centimeter, whole cube by 12 is equal to, we are getting 0.1152 mm per 4. So stiffness of the beam Kb is equal to W by delta. So W by delta is nothing but WLQ by 3A for the cantilever beam load at the free end condition. So W will get cancelled. Kb is equal to 3A by LQ. So 3 into E value they given 2.1 into 10 power 6 into I value whatever find out here by L is nothing but 70 centimeters length of the beam. So we'll get the stiffness of the complete beam element. But we already know in the same previous condition, the beam and the spring both are connected to the series condition. So 1 by K is equal to 1 by K plus 1 by Kb. So 1 by K. So they given the spring stiffness as a 10 kg per centimeter. So here 1 by 10 plus 1 by 2.115, which will find out the stiffness of the beam. So by taking the LCM, we'll find out in the fraction form 1 by 0.5726. By making the reciprocal value K is equal to 1.7464 Newton per centimeter total stiffness of the element system. So from that one we can find out the frequency of the element system, square root of Ke by m. Ke they given, mass of the weight they given already 100 kg. So substituting the 100. So omega is equal to 0.132 radians per second. So time period T is equal to, so you are getting 2 pi by omega. So before finding the time period, we can find out directly natural frequency F is equal to omega by 2 pi. So finding in the H form, it will be reciprocal to the time period. If you make 1 by this value also you will get, or 1 by T equal, so it will get into the natural frequency here. So like this we can solve the cantilever beam problems.